Hello and welcome to the Move Fullstack tutorial. In this tutorial we're going to continue where we left off after we've already set up the front end, we've already installed the CLI, and now we're going to actually start creating code. So the goal that we're going to be working towards here is this place example. This is inspired by r/place from Reddit, and similar to r/place, it's a pixel, it's a game board of 400 by 400 pixels, where anybody can go ahead and just place a pixel, command click, get a little color selector, and just by signing a transaction, it should very shortly get updated on the game board. Yep, right there, we just placed that pixel. Similar to rplace, anybody can place a pixel. However, there is no time limit on placing pixels. This is mostly just for example purposes. This tutorial is going to it's going to focus on how to integrate the contracts with the front end. We're not going to go super far in depth of how Move works or how React works, because there already are actually some pretty good tutorials out there for this. But really the point of this is just to get you from, how do you get these two things working very well together, and how do you think about like architecting like a non-trivial program. So it's totally okay if you see, some pieces of code that you don't understand. Again, I'm going to link to some good tutorials for that in the description. But yeah, so let's get started. So what does it mean exactly when we say that Move is NFT or object-centric? And I think the best way to understand this is to go through an example of how you would implement coin in Sui, which is the native token, versus how an ERC20 works in EVM. So first off, if you've ever used ERC20, if you've ever written an ERC20 in Solidity, you'll know that the way that it stores data is that it just has this, it has this global state space. It's very similar to a language like JavaScript or Python, where it maintains this dictionary of the associations between addresses and tokens. So let's say this is our token dictionary. We'll have that an address, which is the key, and in this example we'll just use a string of ABC, and then this maps to the amount of tokens that address has. So let's say they have 10 tokens. And if we want to add a couple other ones, for examples like 1, 2, 3, 4, 5, 6, let's say they have 5 tokens or they have 20 tokens. And the way that you would implement a transfer is you would do just write a function, and again we're just using JavaScript pseudocode. It's like transfer and to string and amount. This is gonna be like a number. And the way this works, we're not gonna implement this, but the way this works is it looks at your token at the tokens dict, subtracts amount from your balance, adds it to the balance of 2. And this is how it works in Solidity. And what Sui realized is that this is pretty slow because they don't have the guarantee of which, they don't have any kind of restraints on which functions can access which data. So, and because Ethereum and blockchain in general is very distributed, if one function on one machine is trying to access some data and trying to mutate that data in a way that isn't compatible with the way that this other machine, this other validator is trying to modify that piece of data on another server, we run into some conflicts. And that's why there has to be a lot of locks in Ethereum. It has to be very serialized, and that means very slow, right? They have to proceed one transaction after the other. They have a very hard time doing anything in parallel, any kind of execution in parallel. And Sui is optimized, the way that Sui is optimized is that they have as many things as possible run in parallel, which if you've taken any kind of system design course, you'll know that is definitely the way. It's definitely a lot easier to speed up a parallelized system as opposed to a serialized one. So this is how it works in Solidity. Now let's move on to Move. In Move, every single piece of data is associated with an object, which is essentially just an NFT. So let's pretend, and again, it's going to be a little bit weird because we're writing JavaScript, but we're talking about Move. So let's say we have coin1, and then this is going to be an NFT, and inside that NFT, there's going to be a field that has a certain balance value, and this is balance, let's say this is 10. And in this example, let's say that this is owned. This is just an NFT. Pretend that coin1 is an NFT that is owned by 0x ABC. They're owned by ABC. Coin 2 is owned by 1, 2, 3 in this battle of 5. and then etc., right? So if I'm ABC and I want to send 1, 2, 3, my 10 tokens, my 10 coins, what I can do is, since coin 1 is just an NFT, there exists this transfer. There's this transfer function that's let's call it like Sui transfer. So there's this Sui transfer function, and we'll get into exactly how to use this later on in the video. But this is native to Sui, and this lets you move ownership of one object to another account. So I could give them my entire account, or my entire set of coins with the 10 balance. And so, like, let's say after I call the Sui transfer function that's built into Sui move, and 1, 2, 3 owns both of my coins, then they actually, by default, these are two entirely separate objects. They aren't combined into the same piece of data like it would be in Solidity. And this is what allows to keep, it's what allows Sui to be fast, but it also adds a little bit of complexity because it means that your coins aren't always going to be stored in one place. For example, and this means that you have to do things a little bit weird. Like, let's say, for example, I don't want to give them all 10 coins. I want to give them, I'm ABC, I have 10 coins in this object, in this NFT, but I want to pay only 5 of those balance. I want to pay only 5 of those coins to 1, 2, 3. And what I could do is, there's this other function on coin. Again, this is built into move. It's like function split. And this takes in the coins. So it's like coin 1, this is a coin. Again, this is gonna be, yeah. So this is it takes the coin, and it takes the value that I want to split off, number, and it actually gives me back a new coin. And I retain ownership of this BAL. And then I can transfer the second coin that is returned in order to 1, 2, 3. So, make a new coin with 0 BAL. Transfer BAL of coin into new coin. And then afterwards, if I want to transfer that new coin to another person, it's just the same as any old regular NFT ownership transfer, which again is a built-in move function. And then I would move transfer ownership of new coin to person I want to pay. And so, again, don't be alarmed if this is a little bit confusing, because this is very different than it is with Ethereum and Solidity, but just be aware that, again, we have this object-centric data model. So now that we have some kind of idea about how objects work and move, let's go on to thinking about how we want to architect our Sui place example. So in JavaScript, right, if every object, we think of these dictionaries as they're like little NFTs that people can own, we might want to place. The first thing that you would think of is like, well, let's just have some kind of like grid. So we have like a const grid equals, and then in that grid we're going to store the data about the pixels, and this is just going to be like a two-dimensional array. And in JavaScript this is a two-dimensional array, so we're going to have a 400 by 400 2D array, and then we're going to store each individual pixel, and all a pixel is all a pixel is a something called a U32, and a U32 is 32 bits or 4 bytes. And remember, a byte is hexadecimal. It's these 2 characters. So if you've ever played around with HTML, you'll know that they have these color codes. So this is the color code for white, for example. And so if we go back to Sui place, this is the color picker. Let me zoom in a little bit. And if we click on different things, you can see that we get this number. All this is just a number in hexadecimal. And if we can, hex to decimal, if we convert this using whatever website we want online, we can see, yeah, this is just a regular number. And the way that you interpret this number in hexadecimal is that you break it up into these little, you break it up into thirds. So you have D3. What this means is it's RG blue, which stands for red, green, and blue. So this D3 is a number that represents the amount of red that is in this color. And 31 is a number that represents the amount of green. And 15 is a number that represents the amount of blue. But for now, all we have to understand is that this color fits in a 32-bit integer, right? So 2D array of 32. And that means that we run into this problem when it comes to move. And again, because move tries to be performant, we have this constraint in move that can't work because objects have a max size. And the reason why is because, again, we're trying to be very fast and very performant, so we unfortunately do have to place limits on the size of an object, whereas that limit wouldn't necessarily be there in Ethereum. And that max size is 250 kilobytes. And usually in like 99% of applications, this is like not going to be a problem. You're not going to run into 250 kilobytes. This is a lot, right? 1 kilobyte's 1,000 bytes, so that's equal to 250,000 bytes, right? And U32 is only 4 bytes. But the problem is that it's 400 times 400, right? Because this is the dimensions of the grid. So this is the number of pixels that we have. And then the number of bytes that we have, remember a U32 is 4 bytes, so that's 4 bytes per pixel. So this is the number of bytes that we're going to have to run. And so this is 640,000 bytes, or 640 kilobytes. And this doesn't work because the object that we have, this huge array is 640 KB. So this is a problem. So this means that the native way that the natural way, the first thing that you might think of isn't going to work for us, and that's just because we're storing a ton of data. So what we can do instead is we can take advantage of the fact that objects can be owned by other objects. And what we can do instead is we can store these pixels, as we can rename this. Instead, we're going to do like const quadrant. We're going to have all these quadrants. Pixel. And again, this is going to be a 2-dimensional array. And this is going to have a 200 x 200 2D array of U32. And this works a lot better. This is, 640 divided by 4. 640 divided by 4 is just 160 KB, which is pretty comfortably below our max object size. And then because we want these quadrants to be associated together with each other and not just kind of like floating out there independently, we're going to have another object place, and this is going to be going to have all our quadrants. And so we're going to store like quadrant 0, and this is going to be like quadrant 0, so this is going to point to the quadrant. And again, forgive my lack of proper syntax, right? Again, this is just placeholder code. Don't worry about it being correct. Quadrant 1, quadrant 2, in quadrant 3. And so if you think about it, again, going back to the game board, if I reset this, this is going to be quadrant 0, this is going to be quadrant 1, this is going to be quadrant 2, and this is going to be quadrant 3. So when I'm placing a pixel, like let's say right here, really what's going on is I click here, the front end determines, we have the set pixel at function. It determines that we're trying to, we're trying to place it at x value 62 in y value 303, and then in the move code it's going to use the place struct. There's going to be a function on this that's going to determine, giving that pixel value, which quadrant, which object should be associated with that, which pixel grid should store the data, and then we're going to get that quadrant, and then we're going to actually perform the modification on this subquadrant. And the thing to note here is really there's only 2 types of objects here. There's this place, which owns each of these quadrants, and then there's these quadrants which actually own the pixels, and that allows us to get around this 250 kilobyte limit at a cost of a little bit of complexity to the system. So I think at this point it makes sense. Some people viewing might be a little bit confused. I think around what is the difference between this quadrant 0 here and putting a fields on here, right? And I think the natural question is, Well, we have these 4 quadrants that are, I said that they're associated with place, and we're saying that each quadrant is 160 kilobytes. So doesn't that mean that with 4 quadrants associated with one place, doesn't that mean that place is going to have, be well over the 250 kilobyte limit? And that would be true if these quadrants, if we did these quadrants as static fields. I think it's a good time to talk about the distinction between dynamic and static fields. So first off, we have static fields. So let's say that we have some new object. In that object, we're just going to say that it has like a number on it. I guess this would be like U64. We're not going to worry about perfect syntax. It's like A, and let's say this is like a string. Again, we're using U64 is what the type is in move, but we're using this we're using this like amalgamation of move and JavaScript pseudocode, which is fine. It's okay that the syntax doesn't work. So this is what static fields would be. And with static fields, you can just access the field like you would any other field, right? You can do object.a, object.b within move, and it's totally fine. The other thing to know is that this object, right? This object has an ID. So if we go to an indexer and we look up this object by ID off chain, it'll show up as having object. We'll just have the object A and object B right there, and we don't have to run any other RPC calls, and it's just super simple. It's just a simple object to look up, and so that's all good. That makes sense. Static fields are pretty easy to understand. But then we also have dynamic fields. So we create a new object with dynamic fields. So any object can have dynamic fields, but in this example, let's say that we also have another object and that has one. It has one static field with this U64 with this number, and then we're also gonna put some dynamic fields. And so with the name dynamic fields, what that really means is that you can dynamically add and remove and access fields at runtime. So if I have some function, do stuff, I can do things like add dynamic field, add dynamic field to object with dynamic fields. You can do the same thing like remove dynamic field. And dynamic fields they're like a dictionary in Python, or they're like an object in JavaScript. They're just they're an associative array, which means that they're a key value store, and you can give it whatever key you want. So like let's say, well, in this example with the quadrants, we're gonna map the quadrant ID that we talked about before to the actual quadrant object itself, and that's how we're gonna link the quadrant object to the parent object. So like let's say that this object with dynamic fields, let's say this is our place. So this is how we're gonna do place, and place for us actually is gonna have no static fields. But if you pretend that dynamic fields, you can think of these dynamic fields as a static field that is just an associative array, like it's a key value store, and we're going to have the quadrant ID. We're just going to store in this list. We're going to store the key of the quadrant ID to the object ID of the quadrant object. And then when we go to our set pixel, so this function set pixel, what we're going to do is we're going to get dynamic fields, and then we're going to do the place, and we're going to look it up by the key. So like let's say that we have our x, which is a number. Oops. So our x, which is a number, and our y, which is a number, and a z, which is a number, or a color, which is also a number. So what we're doing here is we want to const so quadrant ID. So this is so let's say this is 0, and so given x and y, figure out which quadrant. And this is just some math, some basic coordinate mapping to quadrant ID. And then based on that quadrant ID, we're going to get the dynamic field, which is we're going to get the quadrant, which is stored at the dynamic field index of the quadrant ID. So get dynamic field place quadrant where pixel should be placed, and then we're gonna and then the quadrant. Remember that the quadrant has the quadrant itself has the pixels, and then we're just gonna place pixel on the static field on the vector. Remember this 200 by 200 vector on the quadrant object. So the way that I like to think of dynamic fields is as pointers. And that's because you have to do an operation in move to actually get to the field. And that also works on the RPC level, right? So if you go to query this, if you just have the place, if you were to go on the RPC and you were to look up like what fields exist on this place object, well, you're going to see there's this. You'll find somewhere in there that it says, oh, this object has a dynamic field with a 0, with the key of 0 and a value set to the ID of this quadrant object. And then you would have to do a separate RPC command or a separate RPC lookup on the actual quadrant object ID to get all the pixels, like the 200 by 200 quadrant pixels. And so this design, again, it adds a little bit of complexity, but the reason why we're doing this is because if you think of like a dynamic field as just a static field that holds this dictionary, the place is like a really small object, right? All we have to do is store this basically just a small hash map, right? So we're not really storing any data here. All of the data is actually stored, because it's an entirely separate object, it has its own 250 kilobyte cap. So as long as, because we're doing this association through dynamic fields and not through putting all of the vectors as static fields onto place, we can get around this object cap. But also note that there's the downside there is that instead of doing one RPC request on the object ID to get the whole table, now we're doing 4. When we get around to the front end, we have to keep 4 objects in sync with our front end. So that's the downside. I think it's also important to consider that the point of this tutorial is not to teach you all about the intricacies of move and how the type system works and the different types of objects and how things can be owned, although that is really important. And the reason why is because the Sui Foundation already has some great documentation and some great videos, and I'm gonna put some links in the descriptions to those. For the purposes of time, we're not going to go through all the different types of distinctions. We're just gonna focus on this, and then if you have any questions or if you think any of this is confusing, especially when it comes time to actually programming, I'd really recommend that you go up and look at the Sui documentation and look at their videos, because that's going to clarify things a whole lot. But this was mostly just an exercise for future reference when we're actually going through writing code, like why did we make these decisions. And I think it's important to understand that there is this, we're doing this to get around the 250 kilobyte limit. If there wasn't that kilobyte limit, it'd make a lot more sense just to make a huge vector on place. Unfortunately, we cannot.